Okay, now it's recording. Okay, so again, this is not formally part of the class, this is just the linear algebra review. And so, if you've seen linear algebra before, this is wonderful. If you haven't, I'm going to introduce what we're going to need from linear algebra for linear programming. I'm not going to motivate in any way, shape, or form why we care about that. That will be the lecture when we have everybody. Okay, so what is linear algebra? So what we're looking at is solving systems of equations. And linear algebra is a great way to formalize the process. So for instance, I might give you 2x plus 3y equals 8, 3x plus 2y equals 7. And we have this burning desire to figure out what x and y are. So there's a common way we know how to solve this. This is the method of substitution. So you can either solve for x in terms of y or y in terms of x. So one possibility is to say 2x equals 8 minus 3y, x equals 8 over 2 minus 3 halves y, and then substitute this into the equation here. This is fine if we have a a system of two equations, two unknowns. As we get more and more and more, this is going to become harder to work with. And so what we want is a more formal way of attacking something like this. And then we'll talk about whether or not we expect something like this to have a solution, and if so, how many solutions we expect. So we introduced matrix form. So we're going to write this as 2, 3, 3, 2, x, y equals 8, 7. So again, in mathematics you can define almost anything you want. It's what's a good definition. And so we're defining matrix multiplication as follows. We take the first row here and the column here, and we basically do a dot product. We do first times first plus second times second, and that's going to equal the top component there. So that's going to give us 2x plus 3y equals 8. Over here we'll get the 3x plus 2y equals 7. So we're just introducing a definition. This is how we're going to represent the system of equations. And then the question is, how can we work on this? And so the question is, and this is where I probably should have chosen better numbers, but we'll roll up our sleeves and we'll do some algebra. Let's try to figure out what types of matrix equations are solvable. So if I gave you instead this system to solve, this would not be a hard system to solve. Right? 2x equals 8, 2y equals 7. The equations are basically independent of each other. And this would just yield x equals 4 and y equals 7 halves. Or more generally, if I gave you, ax and dy equals e and f, then there's no problem here. It would just be x equals e over a, y equals f over d. If we try to look at what this would be on the corresponding side over here, we would have something with the form a0, 0, d equals ef. And so we'll call this a diagonal matrix. And basically a diagonal matrix is easy to solve. Okay? So one of the big themes of linear algebra and linear programming is trying to find efficient ways of doing the algebra. If I give you a system of 1,000 equations and 1,000 unknowns that's linear, if there is a solution, you can find it by substitution. You will lynch me before you finish, but you can find it by just substitution. We want a better way of approaching it. So before we solve general equations like this, I want to review something you've probably seen since elementary school, well, maybe junior high, the quadratic form. Right? Everybody should know the sing-song. If I give you ax squared plus bx plus c equals 0, the roots are negative b plus or minus square root b squared minus 4ac all over 2a. How many of you can prove that right now? Kim was not pointing at you, so there's no reason to. So where does this come from? Let's look and see how we would solve the quadratic equation. That's going to be great motivation for how we would solve this. Before we solve the quadratic equation, what equation should we solve? Before we solve something with an ax squared, what should we solve?
Just ax.
Yeah, do a linear first. So let's do a linear equation. So if I give you, x equals b, can you solve? Yeah, it's not that bad, right? It's easy to solve x equals b. X equals? B. All right. Let's make it a little bit harder. Ax equals b. The solution? X equals a. B over a. Yeah, see, it's getting a little bit more complicated now. Okay. Let's look and see what happens with quadratics. Quadratics is a little bit interesting now. So what's the simplest quadratic I can give you? X squared equals c. That's the simplest quadratic I can give you. There's no linear term, there's no coefficient in front of x squared. And the solution to this is just going to be plus or minus the square root of c. X equals plus or minus square root of c. What's the next easiest quadratic I could give you?
Ax squared?
Ax squared. Finish it.
Plus b.
No, not plus b. Ax squared equals c. That's the next easiest thing I can give you. Once I give you this, we reduce this to x squared equals c over a. We know how to solve something of this form, right? This c over a is playing the role of the c from before. Therefore, x equals plus or minus the square root of c over a. So the goal is always to reduce things to previous problems. So now if I give you ax squared plus bx equals c, the question is, how do we attack this? What we want is something on the form az squared equals, I'll say, d. If we could convert this to the form az squared plus d, we could solve it. So what we're going to do is we're going to write this as a x squared plus b over ax equals c. And this is beginning to look like something squared. So we can write this as a x squared plus b over ax plus b squared over 4a squared minus b squared over 4a squared equals c. And so what we've done here is we've said, well, what would we need to get a cross term of b over ax? And so this is going to factor as a x plus b over 2a squared minus b squared over 4a squared equals c. And if we square it out, we get x squared plus the 2's cancel, b over ax plus b squared over 4a squared minus b squared over 4a squared. And so now all we have to do is bring this to the other side, and I'll make a cardinal sin and I'll go backwards to keep it on the camera. We get a x plus b over 2a squared equals c plus, and bring this over to the other side,
plus over 4a.
Over 4a. And now this is our d, and this is our z. So now we know what z is. So z is basically x plus b over 2a. Well, if we can solve for z, then we can subtract b over 2a and get x. So to me, this is the right way to look at solving the quadratic equation. We reduce it to a simpler quadratic which we know how to solve. And this is our guiding principle in linear algebra. So what does this have to do with systems of equations? Well, if I give you a diagonal system where the variables don't know each other, it's pretty easy to solve. So let's think now about what's the next easiest system of equations to solve. So we're not going to jump straight to the very complicated problem I gave at the start of the lecture. So if I give you something in the form ax equals e dy equals f, this is diagonal you can easily solve. A nice tweak is to put in a by here. And if I do something like this, which variable should I solve for first, x or y? Y. I can pick off y easily. Y just f over d. And then I substitute. Just so the record sees I don't know. Plug it in. There we go. And so we get ax plus b times f over d equals e. So the idea is if I have something like this, I can easily solve by going up a level. More generally, if I gave you something of the form 1, 2, 3, 4, 5, 6, and I gave you this system of equations, x, y, z equals 9, 8, 2. We can solve for z first, then solving for z, we would then be able to easily solve for y, and then knowing y and z, would be easily able to solve for x. So a good chunk of linear algebra is actually coming up with algorithms to reduce a matrix to, say, this form. And this is called upper triangular. So upper triangular forms, we should be happy whenever we see. Think of this as looking at a quadratic without that linear term. And a quadratic without a linear term is very easy to pull off the solutions. It's the same thing here. We can just get them one at a time. So there's techniques in linear algebra to reduce any matrix to upper triangular form. I may or may not talk about that later today as to how would you actually do that. But the idea is if we have something of this form, we should be able to solve it. Right. There are two ways to view what a matrix is. One is a way to just encode the information you have, and another is a matrix as a transformation. And so at some point I may talk a little bit about a matrix as a transformation. That's not going to be as important in what we're doing in linear programming as the matrix as a representation of a system of equations. But all of the operations you do to make a matrix into a triangular form like this can be viewed as transformations. And so that is important as well. But let's go back to our equation in the plane. So we had initially 2x plus 3y equals 8, 3x plus 2y equals 7. What kind of object is 2x plus 3y equals 8? What does this represent? So graphically, what would this be? A line. This is the same if you want to write it as y equals negative 2/3 x plus 8/3. And the second one would be y equals negative 3/2 x plus 7/2. Right? I have two lines. I can figure out what the slope is. I can figure out what the intercept is. And I should be able to graph them. Is this part still on the screen over here?
It's almost getting out.
Okay. Well, so let's look for the intercept. So if x equals 0, y equals 8/3. So 1, 2, 3, 8/3 would be a little bit less than 3. I'm sorry. That was y. 1, 2, 3. So if x equals 0, y is a little bit less than 3. If y equals 0, x equals 4. So the first line would look something like this. The second line, if x equals 0, y is 7/2, which is I think 3.5, which is a little bit higher. And then if y equals 0, then x is somewhere between 2 and 3, about 2.5 maybe. And so we see that's the solution. So in general, when you're solving linear systems of equations like this, and the linear means that you don't have any cross terms, you don't have any powers. You would expect there to be 0, 1, or infinitely many solutions. So what we're doing here is basically we have two lines. And we're asking, how often can two lines intersect? Well, it's possible for two lines not to intersect. They can be parallel. Generically, two lines will intersect in a unique point. What happens as soon as two lines intersect in 2 points?
They're the same.
They have to be the same line. So it's possible I could give you the same line twice. And so these are basically the 3 possibilities in a plane. And it turns out this also holds in higher dimensions. Instead of having a line, if we had 2x plus 3y plus 4z, what would that be? So you might remember this from multivariable calculus. It would be a plane, exactly. And so if we added one more variable, we get the equation of a plane. And so if we have 2x plus 3y plus 4z equals 24, just so everything divides nicely. If you want, you could write this as z is negative 2/4, so negative 1/2 x minus 3/4 y plus 6. And one way to see that this is a plane is you have 2 free parameters, x and y. 2 free parameters. And then the third is determined. So when you have a system of equations, essentially the way you should look at it is every equation costs you a degree of freedom. So imagine I don't write any equations on the board, and I tell you, I'm thinking of a triple xyz. What triple could it be?
I don't know.
Are there any constraints on what triple I can think of? No, I haven't written down any constraints. All possibilities are valid. And so, the notation we use is, R is the real line. R squared is the set of all pairs x and y. X, y, and R. And in general, this is stuff in corresponding Rn is all triples x1 to xn. Each xi is real. And so if I don't write down any equations, then my answer, the point I'm thinking of, could be anything. Every time I write down an equation, however, I start to introduce some constraints. And so if I now write down, let's go back to the plane. If I now write down 2x plus 3y equals 8, so I'm thinking of a point, and my point satisfies this. So I initially had a 2-dimensional solution space, and this now restricts me to a 1-dimensional solution space. I've lost a degree of freedom from this equation, which makes sense. I can solve for x in terms of y, or y in terms of x. I've lost a degree of freedom. Now I can do it again. 3x plus 2y equals 7. So I started with 2 dimensions for my possible solution. I then went down to 1 dimension, and then this should bring me down to a point. Now you have to be careful. What if instead my second equation was 2x plus 3y equals 88? Then there's no way, I see head shaking, that this can simultaneously be true. I want my point to satisfy this combination is 8, and that combination is also 88. And so sometimes you have degenerate cases. This is not the typical behavior. And so for those of you who have been either fortunate or unfortunate enough to take probability with me, with probability 1, if you write down any equation, there will be a solution. The problem, of course, is sometimes you could have it the other way, and it's still degenerate. And here I would have infinitely many solutions. Because these two equations are actually the same equation. Now sometimes, we would write it maybe this way. So at first it may look like we have a different equation. But in reality, it's still the same equation. And so what this represents is not changed if I multiply both sides by 10. Now things can get a little bit more complicated. So let's take x plus y plus z equals 4. minus 2z equals 6. So I'm thinking of a point that satisfies this. I start off with 3 dimensions. This kills 1 dimension. I'm down to 2 dimensions left. This kills another dimension. I'm down to 1 dimension left. So the points that satisfy this are a line. Well, if I give you one more line in 3 space, typically those lines will intersect at most in 1 point. Will intersect in exactly 1 point. If we were in the plane, it would have to be. But in 3 space, how likely is it, do you think, for 2 lines to intersect?
Very unlikely.
Very unlikely. But let's see what we have here. So we start off with a plane. So we have 2 dimensions, 3 dimensions, 3 lines. So let's do one more. Let's look at 3x plus 4y minus z equals 8. So I have 3 equations and 3 unknowns. Do we expect this to have a solution? Typically, you would expect this to have a solution. But if you notice, if I take the first one and add it to the second, I get 3x, I get 4y, I get negative z. What should this number be?
10.
10. Since this number is not 10, there's no solution. Because this is really not a new equation. This is really the same equation as these 2 together. So I have not given you any new information. If I change that to 13, now we would expect a solution. Right? And so there's either 0 solutions or 1 solution, depending on what's going on, but almost surely this should have a solution. Okay, so now, let's talk a little bit about bases for space. So I might not have mentioned this in the notes as to what we need, but this is going to be extremely important for linear algebra, for linear programming. So I know this is being recorded, and it's painful for me to say this, but this is how I give this lecture. I am a Bostonian. I love Boston. I hate New York. There are many reasons to hate New York. There are many reasons to love Boston. There is, however, one thing New York, or at least a part of New York City, does far better than Boston. Can anybody guess which part of New York City does something better than Boston? And remember, I'm a mathematician. How many of you have ever traveled in the city of Boston?
The roads are horrible.
The roads are horrible. Comm Ave and Beacon will flip as to which one is above the other. The roads will intersect each other and flip. Boston is horrible. Which part of New York City is well designed?
The roads.
Which part of New York City?
Manhattan.
Manhattan, yeah. You know, it's basically the only nice thing I will say about New York City. You know, they put their city on a nice grid. So if you want to describe where you are in New York City, if you want to move around in New York City, it's very easy. You have your north-south roads, you have your east-west roads. And so you can specify exactly where you are by going, say, go 2 units east-west, and go 4 units north-south. Boston, you can't do that. The roads are horrible. And you know, if you're a pedestrian, it doesn't really matter if they're one-way streets or not. So what we have here is we really have 2 directions. We have the east-west direction, and we have the north-south direction. And the idea is we can represent an arbitrary point as a combination of these 2 directions. So typically, you'll use maybe E1 for the east-west direction and E2 for the north-south. If you were taking multi-variable calculus, sometimes they use I, or sometimes I hat, and sometimes J or J hat. I typically don't like the IJK notation. Why? It's easier to just have indices and subindices on the same level. Especially if you want to go to higher dimensions than 3 or 4. Because then you can just write, a sum of EI, AI, as we'll see in a moment, and not have different letters. And so it does make the notation a lot easier to use e's. And so the idea is any point in the plane is a linear combination of the vectors E1, which is 1, 0, and E2, which is 0, 1. So I can write anything as a combination of these two. And so a general vector xy, I can write that as x times, as the vector x0 plus the vector 0, y. So it's very hard, since I'm assuming everybody has had multivariable calculus, I'm assuming some familiarity with vectors and vector notation. If I'm ever using something you haven't seen, please let me know. But what we're doing here is we're saying the sum of two vectors is just add them component-wise. So this is how much I have in the in the east-west direction, this is how much I have in the north-south direction, the sum is where I am total. And I can then write this as xy is x times the vector e1. I'll do it slowly. X times the vector 1, 0 plus y times the vector 0, 1, which is x e1 plus y e2. So these are two very good directions to use. And so the real definition we need is a spanning set or basis. So we've shown, in quotes, that any vector, any point in the plane can be written as a linear combination. A linear combination means take your two basis, take your two elements, and multiply the first by something, multiply the second by something, and add. As mathematicians, you should be immediately asking, is the representation unique? Is there another way to write xy as a combination of e1 and e2? And so let's consider the following. E1 is going to be 1, 0, E2, okay, I'll call it V1. V1 is 1, 0, V2 is 0, 1, and V3 is 1, 1. Can every vector be written as a linear combination of these three vectors? Can any point in the plane be written as a linear combination of these three vectors? So I want to say, can I solve xy equals a1 v1 plus a2 v2 plus a3 v3? Is that always solvable? Yes. Why? There's a one-line proof.
Because you have all combinations of the vectors. You can times any of those vectors by a variable and you'll get all the possible answers.
You have to be very explicit in how you phrase it. Yes. Don't be stupid, Professor Miller. You don't need to use... I don't need to use...
Base 3.
I don't need to use V3, right? We just showed we can write everything in terms of E1 and E2. Right? So just take A3 equals 0. Right? If I can write everything in terms of E1 and E2, then if I give myself more things to play with, I can't make life worse. Right? So you always want to look for proofs like this. There's a very small, this reduces to a previous case. But now we lose uniqueness. So I can write the vector, 2, 3. I can write that as 2v1 plus 3v2. I could also write it as v2 plus v3. And in fact, you'll see this plus 2v3. You'll see that there's many different ways of writing this vector in terms of combinations of v1, v2, v3. Well, this isn't surprising. How many dimensions is the plane? The plane has how many dimensions? 2. And I'm giving you, in some sense, 3 vectors, 3 different directions. I shouldn't need 3 directions to describe things in the plane. Right? This is where you are north-south, this is where you are east-west, and this is where you are diagonally. You've given me too much information. Do I need to use v1? Could I write any vector in terms of just v2 and v3? Yeah. And so, one way you could see this is, let's say I want to write xy as some number v2 plus some number v3. So I have basically just 0a plus b equals xy, or b equals x, a plus b equals y. Gee, what does this look a lot like? You know, the system of equations we saw earlier. And in fact, this is nice, it's in triangular form. You know, b equals x, now that I know b, I now know a is equal to y minus x. And so we can figure out what the values of a and b are. So it's a nice exercise to prove that everything can be written uniquely. And in general, if I give you two vectors in the plane that are not in the same direction, you can always write everything uniquely. And this leads us to the concept of a basis. And so I'm going to just introduce a bunch of words. And so we'll be using these several times throughout the semester. So a linear combination of vectors v1 through vn is something of the form the sum ai bi I goes from 1 to n. So that's a linear combination. So a set of vectors spans a space if every vector in that space is a linear combination of a set of vectors. So sometimes it's actually useful to have extra information. Sometimes if you're using satellites and trying to find your position, you get more information than you need. So linear combination is just collections of sums of vectors. And then we say that combination is going to span a space if everything in the space can be written. So we just showed the vectors v1, v2, v3 from before span R3. They span R2, they span the plane. A basis has the smallest size of a spanning set. So I'm being a little informal in the definition here. You have some space, maybe it's R2, maybe it's R3, maybe it's R4. You look for a set of vectors that spans it. And then you make sure, is there any set that would work that has fewer elements? If yes, it's not a basis. In some sense, then it has too much information. So a basis is not unique. Depending on the problem you're looking at, different bases are more useful. In high school, you might have tried to find equations of an ellipse. And if I give you the ellipse oriented, with the x and y axis, it's not that bad. This is the x over a squared plus y over b squared equals 1. If I give you the ellipse oriented like this, however, most people did not learn how to do this in high school and to write down the equation. Right? If you look at this problem, though, it should be clear that we have chosen a horrible basis. We should not align our basis along the x and the y axis. How should we align our basis? We kind of lean back like this, right? This is what we want to do. Someday I'm going to fall down when I get this up. This is how we would want to choose our basis. So if we call this the xy basis, and we call this the uv basis, the ellipse is very easy to write down in the uv basis. And the idea is find the equation, the uv basis, and then figure out how to transform from the uv basis to the xy basis. And if we can figure out how to do that, we're in great shape. Okay, so in R2, both xy, the x axis, y axis would be a good basis, or for this problem, this would be a better basis. but all the bases here will have two dimensions, will have two elements. This is something that has to be proved. It should be intuitively obvious, right? If you're in R2, if you're in a plane in two-dimensional space, you have two directions. If you're in R3, you have three directions. And your bases should have three elements. If you think about it, one vector, all of its linear combinations gives you a line. Two vectors gives you a plane. And then your three would give you a hyperplane, and so on and so on and so on. Okay, any questions on what we've done up till now? Okay. So this is a lot of the beginnings that we're going to need for linear algebra. A big part is going to be, in some sense, solving matrices and solving systems of equations. There's lots of techniques that are developed in linear algebra to actually do the solving, but in some sense we can take a lot of this as a blank box. The last thing I want to talk about briefly is multiplying matrices. So let's say I give you two matrices, 1, 2, 3, 4, and 1, 3. So not all matrices have to be the same size. So this matrix, it has two rows and it has two columns. So we call this a 2 by 2 matrix. This matrix has two rows but only one column. It turns out you can multiply matrices so long as those two numbers are the same. And so in general, if you have a m by n and an n by r matrix, you can multiply because these are the same, and it's going to lead to an m by r matrix. And so we get to choose how we define matrix multiplication. Well, we were using this to attack systems of equations. And so in what we were doing before, this was 1 times 1 plus 2 times 3, 3 times 1 plus 4 times 3. Right? That's what we had it represent. And so this seems like a really good definition of multiplying this vector by this matrix. Okay? So now, we need to figure out what's a good definition if I give you 1, 2, 3, 4, and give you 1, 3, 2, 4. Ugh. I want to give this interesting. I want things to be a little bit 8, 7. Well, if we didn't have the 8, 7 here, we would just multiply that as before. If we didn't have the 1, 3, we would just multiply it as before. So what we're going to do is, this is going to give us the first column of our new matrix. And then that will give us the second column. So this would be 1 times 1 plus 2 times 3, 3 times 1 plus 4 times 3. And then the second column would be 1 times 8 plus 2 times 7, 3 times 8 plus 4 times 7. That seems like a really good definition of matrix multiplication. Is we were looking at this as, system of equations, evaluating it at this point, system of equations, evaluating it at that point. So we're just keeping track of what goes on. And so if you had more columns and elements, it would just be analogous. And so in general, if you have a matrix A here, and a matrix B here, and you have a matrix C over here, the ijth entry of C, what you do is you take the ith row of A, and you take the jth column of B, and you multiply. So Cij would be the sum. It goes from 1 to n. And again, I'm going to assume this is m by n, and I'll assume this is n by r. It would then be A, I, K, B, Kj. So writing it out, it would be AI1, B1j, plus AI2, B2j, plus whatever. Because I have an I for each of these, this means it's in the ith row. First element of the ith row, second element of the ith row. Because all of these end with a J, it means I'm in the jth column. First element in the jth, second element in the jth column. And so this is a good definition of matrix multiplication. So we have 2 minutes left. So the last question would be, how do you choose to multiply general matrices? Well, we've just decided that this is what it should be. There's an interpretation of this as well. And the interpretation is that we have a transformation. And if I compose two transformations, there should be some new transformation that's the same as both of them. So think of it as, I have a function f, and I apply my function f. I have a function g, and then I apply g after applying f. There should be some new function, h, which represents f followed by g. And so it turns out that when you have these matrices, you can regard them as transformations. And there should be some matrix that represents these two transformations together. Okay, so we can hit the red button carefully. And so what I'll do, well, not so carefully.